Hi everyone, we're going to be looking at exponential growth and decay today, and we'll be looking at section 16D in your textbook, the MYP5+. We'll look at some examples and we'll get our work done. Alright, so let's just start with some basics about exponential growth and decay. Let's talk just a minute about the applications of exponential functions. I mean, we've talked about exponential functions. We know what the graphs look like now, how they move to the left, right, the transformations, vertical and horizontal translations. We've looked at the vertical and horizontal stretches. We've looked at the reflections over the y-axis, over the x-axis. So now we're going to just take a look at trying to figure out, well, how useful are exponential functions? And they are extremely useful in that some of the real-world phenomena in which we can find exponential functions, such as of growth and decay, would be something along the lines of population growth. We could be looking at compound interest in finance. So that's something that we'll be looking at in the next lesson. We could be looking at radioactive substances that are decreasing exponentially as we look at the half-life, and I mentioned this in class as well. And if we were to just look at, for example, in physics or in chemistry or so forth, if we were looking at the temperature of a cup of coffee, for example, and we were trying to let it cool to room temperature, there would be, in that cooling process, we would be looking at exponential a decrease exponentially or exponential decay as the coffee is reaching room temperature. All right, so just very quickly, just returning for a moment to the radioactive substances. Now, a substance that would undergo radioactive decay is said to be radioactive. Now, the half-life, that's something that you may be familiar with, some of you who are taking chemistry. The half-life of a radioactive substance is really the amount of time that it's going to take for 1/2 of the original amount of the substance to change into something else. So after each half-life, the amount of the original substance is going to decrease by 1/2. Okay, so some of those things are things like polonium or plutonium, uranium. They have a very, very long half-life. We're talking about hundreds and thousands of years to reduce by 1/2 the number, the weight of a substance. All right, so let's take a look at our first example. So it says, the exponential increase of a population on a Pacific island since 1970 can be modeled by this function. Okay. So we know that the population increase, okay, is equal to 2,500 times 1.2 raised to the power of 0.3t, where t, in this case, which is found in the exponent, so this value of t here is the time. Okay, so we're looking at time. Okay, so t is the value of the time, or the roll of time. So that if I look at after 1 year, what's my population going to be? After 2 years, after 3 years, I would just plug in the value of t into the exponent, and I would get my value of the population at that time, after 1, 2, 3, or 4 years, etc. All right, so before we do anything, because it says to draw the population graph from 0 to 50, and the population for the time, and the population would be going from 0 to 40,000. All right, so the first thing I would do is I would try to analyze this graph before we even graph it, okay? So I would analyze the function. So taking a look at the function here that's given, 2,500 times 1.2 to the power of 0.3t. Now, the first thing I notice is that my value of the b, so my value of the b is the actual growth factor. Here's my growth factor. So this is telling me if my graph is increasing or decreasing. So since my value here of my value of a is greater than 0, then I know that it's going to be exponential growth. So I do have certainly exponential growth. Okay? So once I know that I've got exponential growth, I now take a look at the exponent, and I know that my exponent is t over or 3/10 t. 0.3 is the same thing as saying 3/10 t. So I've really got 1.2 times 2500, all right, all raised to the power of 3/10 t. All right, so I know that there's also a horizontal stretch, okay, and the first thing that I should notice above anything else is that my y-intercept, or when my time is equal to 0, so if I set this t equal to 0, then 0 times 3/10 will bring me to 0, and then 1.2 raised to the power of 0 is 1. So what that tells me is that the initial amount at time equaling 0 is going to be 2500. So at time equaling 0, my graph is probably going to look something like this. I know that starting at t equaling 0 and then going up every so often of 10, 20, 5, 10, 15, 20, whatever it is, okay? But I know that at 2500 the time is equal to 0. So that's my initial amount. I always see that my vertical stretch is the initial amount at t equaling 0. Okay, at time equaling 0. So what I need to do is I need to do the population graph for the time versus the population. So time is my independent variable, and my population is dependent on the time. Therefore, I've got t on the x-axis and p of t on the y-axis. Now, this is not unlike what we did with quadratics and figuring out what was going to be on the x and y-axis. So your independent variable is on the x, time, and the dependent variable, the population with respect to the time, is going to be your y, because y depends on x. All right, so I'm going to start simply by graphing. So from 0 to 50, and I've got to do a population of 40,000. All right, so I have the graph here already, and what I did was I took 1970 as being my year 0. Okay, so 1970, and then I went up by 5s. So I went to 1970, 75, 80, 85, 90, 95, 2000, 2005, 210, 2015, and then 220. Okay, so that, let's see what the actual graph said. It said to go from 0 to 50, and I did that. I went along the x-axis. I went from 0 to 50, and I did that going up by 5s. Okay? And then it said to go from 0 to 40,000, and I decided to go up by 2500s on this. So I went up to 2500, 5000, 7500, 10,000, etc. So I went up by 2500. Now, you are free to go up as you please, like on the scale. Just be aware that you can't be going up by 1s or 10s, but you're going to have to use some larger numbers here. So you're going to have to figure out the scale that you want to use, as long as you get to 40,000. Okay, so what I did was I took a table. I made a table, and I said time versus the population. And I picked particular times. I picked 0, 10. I could have picked 0, 10, 20, 30, 40. I could have gone up by 5s and just done 0, 5, 10, 15, 20, 25, 30, 35 if I had wanted to. And then just plugging these values into my calculator, I could have very quickly gotten my, my values of the population based on what the value of the time was that was inserted in here in the graph. Okay, so in the equation. So I just plugged in the value of t, and I was done. So basically what that means is if I'm just going to take one example here because this has already been done for you. So I'll just take one example. We'll do p at 10. So that goes to 2500 times 1.2 raised to the power of 0.3 times 10. Okay? So what that means is this is going to go to 2500 times 1.2 raised to the power of, well, 0.3 times 10 gives me 3. I then do 1.2 raised to the power of 3, and then that gets multiplied to 2500, and that should give me 4,320. Okay, and that's what I did all along here for the rest of them. Afterwards, I'll show you how to do this just on your calculator so you don't have to work it out individually for all of them. Okay, so let's take this example here. And so here's our graph, and you're always going to graph time in years. You'll put your population, or P of t, over on the y-axis. You're always going to label your x and y axes. All right, so time and population with respect to the time. And we're done. So we've graphed the first part. Now, that was the first part, part A. The second part then says, use the graph to estimate the population of the island in 1970. All right, so in 1970, well, that should be quite simple because it's going to have to be exactly where 0 is on the y-axis, so that it's going to be at 2500. So when my time is equal to 0, my value of the population is 2500. All right, the next question then says, use the graph to estimate the population of the island in the year 2000. All right, so if we try to do this, oops, I went ahead. If we try to do this, now I went 2 back. Okay. So if we try to figure out what it's going to be in the year 2000, okay, so that means that what I would do using my graph, all right, is I would go along until I hit 30 years, because 1970 plus 30 gives me 2000. And then at 30 years, I would go up the graph. So I would basically do this. I would then take, at 30 years, I would go back up, and then I would go back to my y-axis to find what the corresponding population is going to be at 30 years. So I'll go up along the y until I hit the graph, and then I will go along the x until I see what my value is going to be. And it would appear that my value, well, I've got 10,000 here, I've got 15,000 there. In between that will be 12,500. It seems just a little bit more than that. So the approximation could be approximately 13,000, our population. Now, if we wanted to figure out exactly what it was, well, we'd have to go about that a different way. And I'll show you in a couple of minutes how we would do that as well. Okay, so the next thing that you're asked is the first year that the population of the island will be greater than 34,000. All right, so greater than 34,000, if 34,000, so 34,000 is approximately here, and again, remember, this is approximating. So 34,000 would be approximately there. If I take that along now, the graph along the x, and then I come down along the y, well, it looks like it could be about 48, approximately 48 years it could take. So that means that 48 years later would have to be from 1970 to 2000 would be 30, and then another 18 would be 2018. So it looks like it could be approximately the year 2018 when we are looking at the growth of the Pacific Island being approximately just greater than 34,000. Now, if we had to do the same question precisely, meaning that I wanted to have the precise values of the population of the island in 1970, of the island in the year 2000, and the first year that the population of the island will be greater than 34,000. All right. Well, what I could do is I can open up my calculator. All right. So in showing the calculator, let me give you a quick explanation on some of the things that we can do with the calculator. The calculator can be very powerful in exponentials to help you solve the equations. Okay, So what we want to do is we want to graph this function 2500 times 1.2 to the power of 0.3t. So the first thing I'll do is I'll press the y equals button, and I'm going to place in there 2500 times bracket 1.2, close the bracket, raised to the power of, now I would place brackets in there, 0.3 times x, and then I would close the bracket. Enter. All right, now I've placed the graph in there. Now what I'm going to do is I'm just going to go to graph right now, but I'm going to show you that it's not going to work. Okay, so you're not going to be able to see anything here. And the reason why you're not going to see anything is because we don't have the right window. Now, because they have told us what to use for the window, I'm going to go to the window button now. I'm going to go to the window button now, and I'm going to change my window. So I'm going to start with my time, or my x values along the x. I'm going to start at time equaling 0, and they told me to go all the way up to 50. Now, how I choose to go up is really up to me. Maybe I'll go up by 5s, as I did on the actual graph before. Now, my y minimum, I'm going to start that at 0, and I'm going to go up to a maximum of, well, it's got to be 40,000. And the y scale, I said that I would go up by 2500s. So, I mean, again, I could have gone up by 1,000 if I had wanted to, but I decided to go up by 2,500, or I could have gone up by 2,000 or 5,000. Really, it's up to you to decide. Enter. And now I'm going to graph. Okay, and as you can see, the graph is slowly coming up. Okay, all the way up to 40,000. All right, so along the x-axis, we've got the time. Along the y-axis, we've got the population. Now, the question is asking to find the population of the island in 1970. So in 1970, it would be when time is equal to 0. So one way I could go about doing that is by going to the second function, calculate button, and I could press the value button. So press enter and value. And that allows me to put in there any value of x I want. So if you look underneath here, it says x equals, and if I place that equal to 0, it tells me that 2500 is my value of the y. So that I know that my value of the y here is 2500. All right. Now, if I wanted to do this again, if I wanted to do this again, I could then go again back to the second function calculate button, and I could go to the value once more, and this time I want to put in the population of the island in the year 2000. I obviously mean 30 years later, so I'll put in a time, or a x equaling to 30. And what that turns out to be is 12,890, I can't read it. 12,000, well, I'm sure you guys can see it. It's 12,000, I think, 899.461, so that I will place that in there. So it's 12,899.451 or 461, so that I will place 12,899.461. That's interesting. 0.461. So I know that my population in the year 2000 is going to be 12,899. And the very last question asks you, for the first year that the population of the island is going to be bigger than 34,000. So I'm certainly not going to be placing in here, again, I'm not going to go to the second function button and then put in value again. Okay, because putting in value again means that I would be putting in there 34,000, and that's incorrect. The first year, they are giving you the population now is 34,000, and they want you to go back, and they want you to figure out what year would it be, or how many years would have gone by from the original 0 year of 1970, in order for it to get to a population of 34,000. So if I can't use this form, but what I can do though, is I can find the point of intersection between this graph and if I go now down to the second slot down here, what if I were to just place in there 34,000? 34,000 is going to be a horizontal line. So when I place in there 34,000, you can see that the point of intersection is up here somewhere. All right, so our point of intersection is up here. Okay, we can see that it's up there. It's right up there between the red and the blue curve, between the red line and the blue curve. So that what I can do now is I can go to second function calculate, and instead of looking for the value, I could look for the point of intersection. So I press 5. So I did second function calculate, and I go to 5, number 5, which is the point of intersection. Now, we've done this many times before, where you are looking for the point of intersection between two curves or two lines or whatever. And the first thing that it's asking is, you can see that the cursor is on the first curve. My tendency is to get it a little bit closer to the point of intersection. So I'm going to bring it a teeny bit closer. And now it's asking me if this is the first curve, and I press enter, and it fixes the point there for me. The cursor then moves on to the next line, and the next line again, even here, I'm going to move it a little bit closer, but it's not absolutely necessary. And now I'm going to press enter again, because it's asking me, is this your second curve? And I say yes. Now, by pressing enter. Now, the question that's being asked is, should the calculator take a guess now that it knows what the 2 points are that you're going to try to get closer to? And the answer is press enter again to yes. And it tells you, if I press enter, it tells me that the intersection occurs at 47.7 and 34,000. So 47.7 would have to be where, so that would be 47.7 years, okay? But since we are going to just round up to the number of years, and it has to be greater than 34,000, and this also gives me what it's equal to 34,000, so I'm just going to say that it's going to have to be greater than, it'll have to be approximately, if I just round this up to 48 years. All right, so that's how you would work this question out, okay? Now, the other thing that I promised I would show you was that if I had to, so let's go back here. I'm going to remove the 34,000 from the graph. Now, what I can also do is, instead of working out the table as I did over here, you see that we have the table with 0, 10, 25, 30, and 35. What you can actually do is you can place the function inside the y equals on the calculator, and what you can do is you can go to second function and table. All right. Now, here's my second function and table. Notice that it's giving me all the values of x and all the values of y that correspond to that function. So when I placed in the value of 3, my value for x, 3 years, the value of y is 2,945. Now, if I were to go down to, let's go down to the 10 years that we looked at before. So the 10 years was right here where we had looked at it, and we said that it was 4,320. We figured it out manually, algebraically, but the calculator could be doing this for you. Now, if I wanted to get to, I'm curious now to figure out how many years, if I were to go up, so we could actually guess. We said 30 years later. So 30 years later for part B was, what's your population going to be 30 years later? Let's take a look what the actual amount is going to be 30 years later. So we get to year 25, 26, 27, 28, 29, and where's my year 30? Oh, look at that. It's 12,899. Now, when we estimated it to approximately 13,000, which is quite close to what we originally, to what we estimated. So we estimated 13,000, and the actual amount was 12,899. So that's one way of going about doing this as well. I could go onto the table and go to year 30. Now, if I wanted to know For example, where it first hits 34,000. Let's see how correct we were at 34,000. So I'm just going to keep going up here until I find a y value that hits 34,000, approximately 34,000. So I'm just going to keep going up, and I've gotten to 25,000, 26, 27, 29, 30, 34. Let's see. And here it is. Now at 47,000, we've got 32, approximately 32,689. And when I get to 48,000, there it is. It's 34,526. It's just over the 34,000 mark. And it was exactly what we said it was. We did it though with the graph. So we found the point of intersection with the graph. But as you could see, I could have just scrolled all the way down the years, all the way down the populations until I hit a number that was over 34,000. The only drawback of doing the problem this way is that when I'm looking for the number of years, if I don't have the correct intervals, so what, since we found that the actual amount was 47.7, but I didn't go up to 47.1, 47.2, 47.3, and so forth. I just did 47 and then 48. So it could have been a value between 47 and 48, which it was 47.7, but then we rounded it up to the next amount, which was the next whole number, which was 48 years. We're not going to be looking at 47.7 years, we'll be looking at 48. All right, now, which brings me to another thing, in that I could also change how the table is set. So if I press second function and then table set, notice that the table starts, now the table setup gives me that the table is starting at 38. Well, how about if I have it starting at 0, and instead I have it going up by 1s, but you see that I could have it be going up by 0.1, or I could have it going up by 0.5 if I wanted to. That would make it extremely long and very complicated. So I would tend to go up by 1, but it doesn't mean that you can't set up your table so that you have it in increments of 0.1 or 0.5 or whatever it is that you choose to use as your increments. So we press enter, and the table is going to be set up exactly the way we had it before. So there it is, from 0 all the way up to infinity if we want. Okay, and I could place, I'm not sure if I'm allowed to do this, but I don't think I can. I wanted to see if I could scroll down a little faster by placing in my value of x, but I can't seem to do it with, at least not with this calculator here on the screen on the computer. All right, so that takes care of one type of question. All right, so let's take a look at some other questions. Okay, and this was an example of when I used the calculator, but the one that I showed you is far better than this. All right. So this is the whole explanation. Let's take a look at the next question. And the next question says that you have a sample count of bacteria in a culture that indicates that the number of bacteria is doubling every hour. So every hour the bacteria is doubling. Now given that the estimated count at 3 p.m. was 12,000 bacteria, what they want you to do is find the estimated count 3 hours earlier when it was 12. And they want you to write an exponential growth function for the number of bacteria at any 1 hour. Okay, so because it's doubling at every hour, then the population of the bacteria will equal 2 to the power of p. Remember that the value of A is your growth factor. It's determining whether something is growing or whether something is decaying. So P equals 2 to the power of T, where T represents the hour and P is the population. So all we have to do now is just go back, okay? So if I know that at 3 p.m. my number of bacteria were 12,000, at 2 p.m. they had to be half as much, not doubled, but half as much because we're going back an hour. So that by the time we get to 1 p.m., that one is the 6,000 bacteria is now going to half to 3,000. And then the 3,000, by the time you get to 12 p.m., which is now 3 hours earlier, it'll go from 3,000 to 1,500. So the number of bacteria at 12 p.m. would be 1,500. Okay. Now, let's look very quickly. Let's look very quickly at exponential decay, where we're looking at the half-life of a radioactive carbon-14. That's approximately 5,730 years old. Okay. Now, it's saying, when you have a 10-gram sample of carbon-14, okay, so how much of a 10-gram sample of carbon-14 is going to remain after 15,000 years? So they want to know how much is going to be left over after 15,000 years. All right, so in working that out, so what we have is, using our formula, y is equal to b times a to the power of t over n. Now, here we have the formula for exponential decay. So this is my starting amount, 10 grams, is my value of b. My value of a is going to be the half-life, so it's going to be 1/2. T is in the exponent is the number of years, okay? And since we're halving this, okay, so every time, so t is my number of years, and 5,730 is our half-life. Okay, so I made a mistake in saying what I said before. Our half-life is 5,730. All right, so what we have then is that we've got 15,000 divided by 5,730. That gives us a 2.617. Therefore, when I raise 0.5 to the power of 2.617 and then I multiply it by 10, that ends up giving me 1.63 grams. So what does that mean? It means that if I were to take a 10-gram sample of carbon-14, okay, and I let 15,000 years pass, that would mean that what would remain would be 1.63 grams of that 10-gram sample, okay? So that's how long it takes for carbon-14 to decay. All right. This one we are going to do in class, so I'm going to just stop right there, and we'll be looking at this thoroughly during the class. All right. Talk to you soon.